We finished the previous session with a question. How do you distinguish between the behavior of a Turing machine that is in an infinite loop? So that it will just never end up in a halting state, in an accept state, Q accept, or a rejecting state, Q reject. It just never do that. So how do you distinguish between that situation and a situation where the machine is just taking a hell of a long time to compute, but that it will eventually arrive in a halting state, Q accept or Q reject. So how do you know the difference? So that's that gets subtle and it can be difficult. So to just avoid the problem, supposedly, and I have a question mark about this, but so Sipser is proposing a subcategory of Turing machines that are labelled deciders. Okay, deciders, and they are machines that they halt on all inputs. That seems to me a bit of a contradiction, because in the next chapter we will show there are languages that are undecidable. Anyway, so this part here, I have a real question mark about, and perhaps it may be interesting for you to return to this part after you've done chapter 4, the next chapter, because that halts on all inputs. I feel antsy about that. It seems to me that idea is contradictory to the idea that there are inputs that cannot be decided, like the famous halting problem of Turing that we're approaching now. Okay, so anyways, so for what it's worth, talk about Turing machines now that do halt on all inputs. So they either reject or they accept, and that's it. There's no looping. Okay, so we're talking about such machines. They either halt. Sorry, they either accept or reject, but they always halt, on all their inputs. And such machines that do that are called deciders. Okay? So that they always make a decision to accept or reject. They always come to a halting state eventually. It may take a long time, but they do it. Okay? So you're talking about such machines. So if you have a decider Turing machine and it recognizes a language, in other words, it accepts all the strings of that language and rejects all the strings that are not in that language, okay, then if the Turing machine that's doing that is a decider, then that machine is deciding, it decides the language. Okay, so more definitions. Alright, so here's another formal definition, 3.6, chapter 3, the sixth thing in the chapter, given an integer ID. So a language is called Turing decidable, or just simply decidable. You tend to abbreviate it after a while. If some Turing machine decides it, okay. So you have a language, you have a Turing machine that decides it. What that means is it will accept every string in the language, and it will reject every string that's not in that language. Okay. Well, you may ask, well, what's the what's then? But that's what recognize means. So what's the difference between deciding a language and recognizing a language? Things get a bit subtle. Okay. So that's a question I ask myself. What is the difference between these two? Well, they're doing the same thing effectively. They're both accepting and rejecting strings. I suppose The only difference is the type of machine that you're using, right? So if you're using a Turing machine that is not a decider, then I guess it's possible that some of the strings that go into that machine, the non-decider, loop. I guess. I mean, that's my thinking of what's being said here. So, what do you think? All right. Okay. Now, it won't be on this board, but starting next board, we'll do the first of 4 examples of actually using Turing machines to compute with. We'll have 4 different languages, and the machine will decide them, meaning it will accept all those strings. So, we'll give starting next board, we'll give actually 4 examples of decidable languages. Meaning that there is a Turing machine, it's a decider type Turing machine, right? Such machines, remember, always accept or reject. Boy, do I have a big question mark about that, given what's coming in chapter 4. I'm wondering, is this another foul up on my part, or Sipser's? I'm puzzled. Right. Okay. Now it says here. This is why I query. Am I missing something, or is Sipser fouled up again? I get annoyed that this sort of thing keeps happening. I mean, now Sipser did foul up, I think, on the pumping length thing. He gave 2 different values, which confused me totally for a while. Okay. Right now he's stating here that we'll present, we'll show you languages that are Turing recognizable. Now we'll go back to the previous session. I'll read it out for you. You can't see it, but definition 3.5, it's 3.6. 3.5 says a language is called Turing recognizable if some Turing machine recognizes it. Okay. And this one's a variation. Language is called Turing decidable if some Turing machine decides it. Okay? So you need to be conscious in your head of the difference between deciding and recognizing. Okay? I think the difference is subtle. Anyway, later the text will show you that there are languages that are Turing recognizable but not decidable. Now, good luck with that. Things are getting subtle, right? So, that's the kind of logic inclusion. For example, all people who live in Xiamen, that's the city I live in, all people who live in Xiamen live in China, but not all people who live in China live in Xiamen. Okay, so it's that kind of thing. So, now he states here, every decidable language is Turing recognizable. Now, is that supposed to be blindingly obvious, or is it an interesting fact that's being thrown at us that maybe later we will see is true? Now that I'm conscious that Sipser is an MIT professor, I'm now more inclined to think perhaps to him it's blindingly obvious, but not to most. Anyway, so there's something to think about. Is that something that's fairly obvious, or is it something that it will become clearer as we move on? All right. Now.